All right, it's 5:30, so we might as well go ahead and get started. Hey everyone, I'm Mr. Younger. I teach physics, astronomy, and math here at TCC, and I will be posting this video later on my YouTube channel. So if you guys have any objections to your name, your first name, your last name, or even your face being shown, you need to let me know that via email, and you also need to go ahead and change your username within Zoom to something, less critical. So, for instance, if you don't want your name being seen, you might just say Steve N or B Billy Y or something like that. Rather than your actual name. And then, of course, every day when you first get in, your job is to go ahead and chat me your first and last name. That way I can identify who that is with regards to your username. As I said, again, all of these videos will be posted on my YouTube channel. They usually don't show students' faces, but occasionally a student's face will pop up. Occasionally a student's name will pop up. So if you have any objections to that, one, you need to go ahead and send me an email letting me know that that's a problem for you. And then two, you need to make sure you change your username within Zoom so that if it does appear, it won't be seen. I will do the rest from there, but you definitely got to make sure you change that. The other thing I want to let you know, because y'all don't have your syllabus yet, I'm having difficulties rendering the syllabus. We have a new syllabus maker, and I'm having some difficulties with getting it to load up into Canvas. So hopefully I'll have that posted tonight or sometime tomorrow at the latest. But one of the things I tell you in your syllabus is that whenever you email me, you need to email me and my email address. I don't like to say it out loud, obviously, on YouTube. So I'll type it into the chat section right here so everybody will see it. Uh, but this is my email address. And you can see that's related to my name. Of course, I go by Billy, but William's my first name. So you can see that's my email address. When you email me, you need to only email me from your TCC email account, which is a Gmail account, but you need to email me from that. Your first part of your subject line should always say uh, 241 online. If the subject line doesn't begin with that, there's a good chance I'm never going to see it. Okay, so the first part of your subject line, even if you're replying to an email to me, that means you have to either erase the existing subject line or click to the left of it and then type in 241 online, and that has to be on there or I'm not going to see your email. And then thirdly, you have to, in addition to using your TCC email account to email me, and in addition to starting off your subject line with 241 online, you also have to give me your first and last name in the email. If, on the other hand, if you end up sending me an email and then I don't reply to you within one school day. Now, what one school day means is if you email me at any point in time, for instance, on a Monday, then my job is to reply to you by 11:59 p.m. on Tuesday. However, if you send me an email at any time on Friday, then I have until Monday at 11:59 p.m. to email you on a normal week. That's the general rule. So whenever you don't get a response from me, the first thing you need to do is check your email because I might have sent a generic response to everybody that addressed your question. Because a lot of times I have several students asking the same question, and rather than sending each one a personal response, I will send out one blanket email to the class that answers the question. So that's the first thing you want to do. But then if you've done that and you don't see where I addressed your question, then it's important for you to get your question answered. At that point, I want you guys to consider sending me a text message. I'm typing in my phone number right now. You're going to send me a text message, and you need to make sure you include what class you're in. So write in 241 online, for instance, and tell me your first and last name. And then you just need to text me. Here's the phone number. I just put it in the chat line. Okay, that's my personal cell phone number. Don't worry about emailing me at 2 o'clock in the morning or 3 o'clock in the morning. That's fine. I have all my notifications turned off. So if you just need to send me a text message and it has to be at 3 in the morning, that's okay. I'm not going to be bothered by it. But that way you can at least get a response. I find it very important that you guys get a response to your emails. But again, either reply to it in a blanket text or a blanket email or a blanket announcement even. And of course, when I post announcements, they're sent to your email as well. But when I do that, then that'll answer your question specifically if I have several students asking the same question, or I will reply to you directly. Okay, so I'm supposed to do that within 24 quote unquote business hours. So if you don't hear from me and it's important, then go ahead and send me a text message. I don't keep your numbers or anything like that. My iPhone remembers them. When you send them to me, it reads your actual text and it says your name and it'll say it's probably such and such. So I do get that, but I don't record it in my contact list, or else my contact list would be 84,000 people, and I just don't want that. So I'm not going to be snooping on you or anything like that. Just feel free to text me. I understand if you don't want to either. That's fine too. But that's your choice. If you need to get to me via email and I don't respond to you within 2 days, within one business day, then your remedy is to contact me via text message. Okay. You can send me another email and I'll probably get that one as well, as long as you do those three things. Remember the three things about sending me email is: one, you have to send it from your TCC email account. Two, you have to start the subject line with 241 online. And three, you have to include your first and last name. If you do that, I should be able to get your email. Now, when I actually do have my syllabus up, it'll be in Canvas, and over on the left-hand side, there'll be a link that says syllabus, and that'll be where the syllabus is. But in order for you guys to understand somewhat about what this course is about, I need to give you a little intro to exactly how my grades work and stuff like that. I basically have a system where your homework, you're allowed to do whatever kind of Google searches you want for that. If you lean on that too much, it will bite you in the rear and actually cause you to do much worse, even though your grades might be better because you always have the quote unquote right answers most of the time, because you've looked them up and that sort of thing. And I'm not discouraging that. I want you to have hundreds. So if you have worked the problem, you've got an answer and you think it's right and you submit it and it's the wrong answer, then by all means do a search and try to find out what the right answer is. Maybe you can figure out what you did wrong and then resubmit it. And the system, the way the homework works is you can still get more credit for it as long as it's before the due date. So that's fine. I don't mind you doing that. And that's a good way of learning. But if your first go-to item is to look up how to solve a problem, then you're shooting yourself in the foot. There's only a limited number of problems we can solve in physics that don't require us to write computer code or use fancy mathematical software and methods of or techniques that approximate the solutions. So we only have a limited number of examples that you can work. And once you've seen the tricks to all those examples, unless you're some kind of savant that memorizes everything that you see, then your chances are you're going to harm yourself, because part of the learning in the physics environment is a modicum of creativity that requires you to figure out ways to solve problems. So try not to use that too much. I'll give you just a background story. I once had a really, really gifted student. The student lived all the way out in Hatteras, for instance, and I was teaching in Elizabeth City, North Carolina. That's a good 2.5, 3 hour drive. However, once a week I came over to Manio, which would cut their driving time down from 2.5, 3 hours to basically around an hour, hour and a half. So I would only get to see the student once a week. The student was very gifted. I'd had him in two classes before, and the student had crushed my curve. They literally had 108 average after I curved it so that I could have more than one A. So the student was very gifted, very talented, very hardworking. Because of the problems associated with that, I gave her my solutions manual, my instructor solutions manual, and I said, here, you can use this. Of course, you want to be careful with it, but use this if you can't get to me in time to figure out how to solve a physics problem. This is written for instructors, so it's not that clear even from that, but you can use it. And about 3 weeks later, the student brought the book back and said, no, I'm leaning on it too much and I'm finding that I'm becoming less capable. So they literally gave me the solutions manual back. That's the kind of student you want to be. You want to realize, hey, I'm leaning too much on these resources, whether it be AI or just Google searches or whatever. If you're leaning too much on those resources, it will harm you. So you've got to not do that. That means what you should do is ideally you want to read the material before I cover it. Obviously, the first day, that's not really much of an option unless you knew that we were going to cover chapter one, and hopefully you read chapter one already. But ideally, that's what you want to do is you want to cover the material before, read the material before I cover it. Two, right after I finish covering it, then you want to make sure that you can go over the examples that I covered and that you can do them on your own. And then three, you want to start doing the homeworks that are assigned in mastering. Okay, there's two homework assignments minimum for each chapter. There's one that's a problem set, and it's just called chapter one or chapter oh 01 homework. And then there's one that's conceptual, and that would be like chapter oh 01 conceptual. So you're going to have that every chapter, at least two. Some of them will have three, some of them will have even more, and there'll be other extra credit problems I assign as well. But the main thing is that homework that's on the mastering website is mostly designed for you to get more, little less on the experience, but more learning than you can get from just the lecture and just the examples in the textbook. So it is usually not that long. Like I try to set it where it's no more than an hour to 2 hours of time required for you to solve them, and that's based on the national averages. But that's really not enough physics problem experience to do well in a physics class. So once you finish doing those, then you want to either start on the what I call the chapter practice. I'll have a chapter practice for each of the chapters, and in it, it's normally like three concept questions and one problem. And every time you take it, it's going to be a different problem each time or a different set of problems each time. That doesn't count for anything. That just gives you more experience. But really, what you should wait for is the practice tests. So I give practice tests, and those practice tests will also, just like the chapter practice, will be in Canvas. And normally they're on the order of 10 questions, somewhere around there, or less, maybe 7 or 8 questions. And they're supposed to take you 15 to 20 minutes to do them. And every time you do them, you get a different set of questions, and it covers all the chapters that are relevant for that coming test, whether it be an online test or a face-to-face test. Not only that, I guarantee that on each of your face-to-face tests, the questions that are on that face-to-face test, 80% of the points will come from those banks that I'm using for those practice tests. So if you take those practice tests enough where you in principle saw all the questions and all got all of them right, then there's no reason for you making less than an 80. So that's reason enough to take the practice test. But because I still have around 40 to 45% of students refuse to take the practice test, which is just insane. This is not the university. This is not the college way. College and university professors do not give you practice tests. That's a high school thing. Okay. I do it because I find that my students are more successful when I do it. So if you ever get an instructor that does that for you in college class, please take advantage of it. I can't tell you how insane that is for you guys to be getting that. But still, in my case, I do promise you that 80% of the points will come from those practice test questions. But also, at the end of the semester, I'm going to take your highest score on each of those practice tests. And if you miss one, that gets a zero. But it's still, I'm going to take an average of those highest scores on each of those practice tests. I'm going to divide that score by 20. So if you had 100, that means you're going to get 5. And I'll take that number of points after I divide by 20, and I'm adding that to your final exam. That's a half of a letter grade on a comprehensive final exam, which counts for like 25% of your course grade. So that's a really, really, really big deal. So there's a very good reason to do it. And I'll tell you, I still have on the order of, out of a class of 24, I might have 4 students that don't take the practice test. And once every other semester, I have maybe one student that doesn't take the practice test and gets an A in the course. Every other student that gets an A in the course really takes the practice test multiple times. Okay, so that is your key to success. And it's your key to success specifically because it's more practice. You really have to master this stuff to be able to succeed in tests and stuff like that. You need to be able to probably work, I would say, at least 50 problems per chapter, but 100 is what I would prefer to say. Okay. I tried to shoot for 100 myself when I was a student, and most of the times I made it, but that's pretty much what you got to do. You got to solve a ton of problems. That being said, at the end of each chapter, there's a bunch of questions, and those can be solved. And that's part of what the homeworks that I do online come from, but some of them are completely different from that. But the main thing is, with those questions that are at the end of the book, at the end of the chapter, the odd ones have their answers in the back of the book. So if you ever find an example problem or if you ever find a problem in your practice test or in your homework, and it looks like one that's in the back of the chapter, then you can solve that one if it's odd, find out what the right answer is, and then see if you did it right. At that point, you then know how to do it. Back when I went to school, that was our only method. We had that, and we had these things called Shaw's outlines, and that was the only way we got to see physics problems solved. The instructors would show us examples, usually the same examples from the book, sometimes some other examples, but pretty much those examples and then the odd problems that we worked in the book were all we had unless we were fortunate enough to have a Shaw's outline. Shaw's outlines, by the way, are still around. They're very, very good. Highly recommend them. For instance, the one for this course, let me get my Rubik's Cubes and various toys out of the way. This is the Shaw's outline that corresponds to this course. It's called Shaw's Outline Physics for Engineering and Science. And basically, if you look on the back, this is some of the courses that there's Shaw's outlines for. And you can see there are a lot of them that are stuff that you would cover in engineering as well. But the way this works is it has pretty much one chapter that's representative of one of the chapters of every textbook at this level, the calculus-based physics course. And it explains that chapter in usually 4 to 5 paragraphs. And then it uses a bunch of examples where they do the derivations that your textbook author would do, but they do them like problems. So they give you a chance to do them yourself if you wanted to. If not, you can scroll to the back of the chapter and see how they actually solve that one. Or usually in some cases, it's literally the problem and then the solutions right below it. And once you get through that part of the book where you're just doing all those derivations, then it's got a ton of other similar questions that have the solutions as well. And then, as if that's not enough, at the end of that, they have even more problems, and those just have the answers, not the solutions. So they're really wonderful. And they normally cost on the order of $16 to $20, whereas the textbooks, probably used to cost before we started trying to streamline them and use open education resources and stuff like that. The textbooks were costing about $280 to $300 for a 2 or 3 semester course. So if you can look at an object that's $20 or $25, that's a real reward. There happens to be another one. Honestly, I'm not that impressed with the physics for scientists and engineers. Shaw's outline, it's good and it covers the calculus-based stuff, but it's not as good as the algebra-based one. So there's one that's called college physics. That's the algebra-based one, and that's honestly much better. But the problem is you don't get any of the calculus in it. So I'm not telling you to go out and buy these things. You can get your local library. They'll order a copy from another library, and you can look them up, or they'll put them on reserve, or you can even check them out. Or you might want to buy them. I bought all mine. And I bought them when I was a student, and I'm looking right now. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I got 12 here in this office, and I probably have another 30 of them in my office at work, all different titles. They have them for foreign languages, they have them for computer programming, Fortran, C, C++. They have them for all the courses in mathematics, calculus on manifolds, topology, linear algebra, all that good stuff. So I highly recommend them for all of it. Now, someone said, and this is Renee. Hey, Renee, nice to see you again. What order would you suggest for the conceptual and problems, or does it matter? I would say the conceptual is something you can start doing immediately upon reading, and you might find that they're a little more helpful if you did them before you did the actual problems, but they're often quite a bit more difficult, even though they don't require math and stuff like that. So sometimes students sort of work them interspersed between each other. So they might work three or four problems from the problem set of homework and then go and do a couple conceptual questions and then go back and do some more problems and then some more conceptual questions like that. I wouldn't say there's one tried and true way that always works. So you're just going to have to feel that one out. But good question. Anybody else have any questions on any of this? Okay, so far as the assignments go, like I said, so you said you would suggest we read the textbook chapter before you teach it in class. Yes, ideally, I would. It would be better for you, even if you only read it once. That's better than not reading it at all. But it's going to take it's going to take some time for you to learn how to read a physics textbook. Let me get to you in a second. Got a stick in my throat. So, here's the deal. When you go to read, you might try to find the worst book you ever found and use a stopwatch and just start reading it and see how far you can get, how long you can read before your mind starts to drift to, think about things you're doing in the afternoon. And as soon as that starts coming up, hit stop on your stopwatch. That might only be in a minute and a half. That might only be 3 minutes. That might only be 5 minutes. That's a pretty normal scenario, especially reading something super boring. So take like your physics book or take Moby Dick or some other literature that you had to read in high school that you didn't necessarily like too much and figure out what that amount of time is. Now, don't deviate from that. Now, what I mean is once you have that time, which might be 2 minutes, might be 7 minutes, might be 25 minutes. I hope it's bigger, but it might not be. What you want to do then for the next 5 to 10 times reading in your book, I want you to read only for that amount of time. And when you're reading, you want to try to predict what the author's going to say, try to guess examples and counter examples. So you're sort of like interplaying, almost having a conversation with the author, even though the author's just saying stuff and you're trying to predict where he's going. That'll make the reading experience more interactive, as well as reading the chapter opening question. That gives you an idea of what things you're supposed to be looking for. So having those little ideas while you're reading will help, but only read for that minimal amount of time that you can read before you get distracted. And then stop, take a break, go solve a physics problem, go work a physics example, go do a math problem, or go get something to drink or read something from another class. Then come back and read again for that same amount of time. Stop, take a break, come back, read again. Do that at least 5 times, but maybe even 10 times. After the 10th time, bump it up by 1 minute and then do that 5 to 10 times and then bump it up another minute. Eventually, you'll get long enough where you can just bump it up by 10% and that'll be a whole minute or more. At that point, you just want to go to bumping it up by 10%. What you would like to do, what I recommend you guys to be able to do is by the end of the semester, I would hope that you can read any crappy piece of writing for 2 hours straight without losing your attention. Okay. I The gold standard for an actual, university educated person should be 6 to 8 hours, other than taking breaks for bathroom or something like that. But if you can get to 2 hours, that would be a monumental improvement. And the reason why is you're going to get somewhere where a college or university professor has a different idea about teaching than you do, and they're not going to care about whether they're good at teaching. And that's not necessarily it's bad. Okay. It's not my philosophy. It's not that's why I'm teaching at a community college level. But there's a lot of people in the university system that believe the university's purpose is not to educate. It's not at all. I mean, it wasn't supposed to be because we modeled this on the German education system. That's where we made the University of California system. And that's also where Abraham Flexner made the Johns Hopkins University as only a graduate school initially. Their idea was the university's purpose is to create new knowledge, period. New knowledge, not new students, not new graduates or anything. They just wanted to create new knowledge. That's the source of knowledge. So their idea was, hey, I present the material in a way that's clear and concise to me, and the students should be able to use that and learn from it. If they can't, they're just not the kind of students that we need. That's their philosophy. Again, I'm teaching at a community college because I don't want it to be that way. I understand it, and I think there's some merit to it because it built Western civilization as it is. But because of that, even if you have a really well-meaning instructor that does want to help, there's still some chance that you're just not going to understand them. So the better you are at reading a science textbook, the better you are at teaching yourself, because that's really the gold standard. You're going to have classes where your teachers are so bad that you can't do anything. And that was mostly the case with me. I couldn't learn mostly from lectures. Most of my knowledge came from, I would go as a sign of respect to my instructors. I would show up for every class. I'd pay attention. I'd take notes. I'd try to ask questions that I thought were relevant. But then I'd never open my notebooks again unless I really, really needed to, and it almost always was not helpful. Then I just open the book and start reading it, or open a book, because a lot of instructors don't even assign a textbook. They'll say, "Oh, you can use any book you want," blah blah blah, and they won't even assign one, and they'll put three or four books on reserve, and that's like the worst thing in the world for me. But either way, that's what you're going to have to do somewhere probably in your undergraduate degree if you choose to go for a bachelor's degree or higher. So this reading will be a strong part of that. The ideal scenario is you can sit down and read something, and then from that reading, learn how to do it. Like, I sat down one time and read a book on wiring and creating a circuit panel in a house. And then I was able to do it. I wouldn't say I'm a professional by any stretch of the imagination, but I can balance a circuit panel, and I know how to wire a house, and I know how to wire things like that. And I'm not, again, not an electrician, but that's the kind of skill you want. And that's really why a lot of employers want college educated people. It's not that, I mean, in some cases it is that they're going to teach you very specific skills, but in a lot of cases it's just that, hey, usually a student that's graduated from a university has learned how to read at some level and can implement, a white paper or something like that on day one. That's, for instance, how I had to learn when I did structural engineering. There's a publication called ASCE 798, which teaches us how to do wind analysis for structural buildings, which is the same thing as lateral loads that you get from earthquakes. But I didn't have a textbook that taught me that. I had to learn it from the ASCE 798, which is like an 8-page paper. And it's got tables in it and all this stuff. And I just sat down and I read it and I learned how. And then I started doing wind analysis and calculating pressures on structures and telling them how many nails we had to have per inch on the sides and how many in the field and all that good stuff. Sometimes I had to spec a 3x4 instead of a 2x4, weird stuff like that. But that all comes from that ability to read stuff. So, anyways, I'll get off my soapbox now, but that is something to shoot for. Try to see if you guys can get at least an hour, but preferably 2 whole hours of reading even the most boring stuff and still be able to maintain your attention. So back to the stuff about the syllabus. So far, I've told you about I have online homeworks that will be on MyLab and Mastering. That's the chapter problems, and then that's the chapter conceptual questions, and that's 2 to 3 assignments per chapter. That is on mastering, but you never, ever, ever want to go to mastering straight from the internet. You need to go through Canvas and then go to mastering. The way you can do that is when you get to my course, you can either click on an assignment in one of my modules. They're not up yet, so you can't see that. But you click on one of those assignments like homework one or conceptual chapter one, you click on that, it'll take you to those assignments. Or in the left hand side, the left column of the home page of our course, you'll see something that says Access Pearson. You can click there as well, and that will take you to Pearson. On Pearson, the only thing you're going to have is a buttload of study material that you can use as you wish, including AI and stuff like that. But again, remember I told you don't lean too much on those resources. You want the creative part of you being able to solve the problem. At least try every problem, working it out from scratch, get an answer before you actually look it up. That would be a good rule of thumb. But all of that will be in mastering, and you get there through Canvas. Everything else will be in Canvas. So the practice test, the chapter practice, the online test, and if I happen to do a Respondus Lockdown Browser face-to-face test, that will be in Canvas as well. So that's where all those things are, as well as the grade book, and those are the things that you'll be graded on. I have a question. Is there a way to access assignment and homework questions from the Pearson app when not near my laptop? Right now, I can only see the textbook. You're supposed to be able to, but I've had some problems with the Pearson Plus app myself. I cannot say that I would support you doing that just because I can't even get it to load my book up. So I've got to talk to my sales rep or anything like that. But you should, in principle, you are supposed to be able to do that completely from your phone, your iPad, or whatever tablet you might have, and be able to access uh, the full items that you would get in mastering. But it's just not been the case in my experience. Okay. So, as I said, those are the assignments. Generally, what it is your conceptual questions, those homework assignments, I usually drop the lowest, and that counts as 5% of your grade. Once I drop the lowest, I take the average. And it's really the weighted average because some are worth 20 points and some are worth 84 points and that sort of thing. So, it really, the 84 point one is, approximately twice as uh, heavy weighted as a 41.1. So in that sense, it's a weighted average. Uh, that's 5%. The online homework, which are the actual problems, they're similarly weighted and they're worth 10%. The online tests are also worth 10%. The face-to-face test, which we generally have three of those every semester, and a final that's also quote unquote face-to-face. Those three face-to-face tests are going to be worth 30% of the course grade. And then the remaining 25% will be the final exam. Okay. Then there's 20% that comes from lab, and your lab instructor is just going to email me with that grade at the end of the semester. I'll put it in. I do not recommend you counting on the Canvas gradebook. There's pluses and minuses to all the settings I have on there. And one of the things that's been happening recently is because I've decided to not put in zeros for missed homework scores until the end of the semester. Specifically, I do that because when I put a zero in there and then a student takes a homework problem or a homework set and does it after the due date, they still get partial credit. But because I put a zero in there, it doesn't necessarily erase that zero. So it makes me have to manually go in and do things. So I leave it off. And then at the end of the semester, once the due date is passed, which for us is going to be like December 6th, I think, that's the last day to turn in any homework. So on December 6th, I go in and I put zeros on all the missed grades, including the extra credits. And the extra credits, I've given you basically what you got, or in some cases, I changed the grade. If you got like a 78 or an 85 or something like that, I go ahead and change it to 100. But sometimes I just leave it as 85. There's no guarantees on that. But as you can tell, I then, because it's extra credit, I increase the number of thrown out homework assignments by one for each extra credit I do. So if you got a zero on that, it wouldn't harm you. That being said, a student will inevitably have like a 90 something the week before the final. I do that, and then their grade drops to a 70, and they're like, what the heck, right? That's going to happen. So what I recommend, you'll see it in useful documents and links. There'll be a module called useful documents and links in our Canvas page, and that'll have an Excel spreadsheet where you can just type in your grades and even the names of the assignments so you keep track of which is which, and it'll automatically calculate your grade for you. I recommend you either use that or just learn how to do your own weighted average, because that's really the fundamental way that we calculate grades in college. It's also the way that your GPA is counted. It's also the way that we calculate the atomic masses that you see on the periodic table. So, anybody taking a calculus-based physics class, they should definitely be beyond the point where they don't know how to do a weighted average. So I would say that's a big, what we call a lacuna in your lexicon if you can't do that, and that's something you need to fix. Okay. Lacuna just means a big hole, and the lexicon means your verbiage or your language or whatever. So, anyways, uh, let me see. That's about it far as the syllabus goes. So the good thing is the online tests, they're completely open notes, open book, they're open internet searches. The only thing is normally I time them and you have a certain amount of time. And if you go over that time, that would take points off. And sometimes I don't even do the time thing on it. But the main thing is I do those online tests every two chapters to give you some confidence going into the face-to-face test. And not only that, you're allowed to take them multiple times, and I only count your highest grade. So usually I give you 3 attempts and I only keep your highest score. And by doing 3 attempts, you get 3 times as many problems you get to see, and you get them graded, and you get, some confidence because heck, I've taken, 4 online tests before taking face-to-face test one, and I scored a 85, a 92, and a 98, and a 90 on that. I feel really good about going into that face-to-face test, and you should because you've done a lot and you've learned a lot. So that's part of why I do that. So your goal is to make sure you don't miss that, but also, again, don't lean too heavily on the resources that I allow you, because as I said, I allow you open notes, open textbook, open any other textbook. You can even borrow the notes from another student. The only rule I try to tell you guys is you're not allowed to look at anything that was made after I published the online test, because that is obviously an easy way to game the system where, let's say Mr. Nelson is an awesome teacher or an awesome student and he goes in and crushes the first online test and gets 100, and then he quickly makes a web page designed to answer all those questions on there, and he makes it, and then you go and look at it. That would be an unfair advantage. So I'm trying to avoid stuff like that. So I say you're not allowed to look at anything created after I post the online test. Okay. That's the major rules. Remember the major one about the emails, the 3 criteria that you have to do. The actual syllabus, when I put it up, it'll have a cut and paste section at the end that you're going to paste into an email, and you're going to answer certain questions and you're going to return that to me. And that's basically the equivalent of you saying, hey, I know here's the syllabus and I'm responsible for all the information in it. And here's some of the most critical information that Mr. Younger's found valuable. And I know how to answer those questions. So you normally that would be due by the second Sunday of the class, and that's basically what's going to happen with this one. I'll post that as well whenever the syllabus is posted, and I'll post an announcement when it is posted, and that announcement will go out to you guys as an email. Anybody have any questions on all that? George did say he was able to do it through his phone, so that's good to know. Thanks for letting me know, George. As I just want to repeat this because some more people came in. This video will be going online on my YouTube channel. That means the whole world can see it. It's not a closed channel. So if you are, in witness protection, you're hiding from the man or whatever, okay, you want to first send me an email and say, hey, I can't have my face or my name posted on the internet, and you need to send me that email appropriately using the 3 rules. And then 2, you need to change your Zoom username to just maybe Billy Y instead of Billy Younger or whatever. So make sure you do that just in case it does pop out up. But will once I get that email, I'll do my best to cut out any of that kind of stuff. And if you see that I missed it, make sure you let me know, and I'll go and take it down immediately. I don't want to get anybody in trouble. I literally have had fellow students that were in witness protection. So I literally had one that was running from the mob. So I, the student couldn't have their name posted anywhere. And I was like, okay, I'll do that. But generally, nobody cares. And by the way, it's on my YouTube channel. And I'm sure you've all heard how famous I am and how famous my YouTube channel is. So you're clearly going to find everybody finding you on there. Yeah, I'm not monetizing. It doesn't have any money. I can't make any money off of it. I do recommend you subscribe to it. I'm going to go ahead and type the URL now. Oops. So that's the URL for my YouTube channel. And yeah, evidently I can't type without my lips going. But anyways, that's my YouTube channel. I do recommend you subscribe to it because sometimes I'll have a little extra time before a test and I'll see students are making a certain mistake and I'll work a problem like that and post it on my YouTube channel. If you subscribed and have your notifications on, then you'll get a notification. Oh, Mr. Younger just posted this on the page, and you can read from the title that it would be helpful to you. So that's something that you probably want. Not only that, if you ever miss a class, there's an exact equivalent lecture to the one that you missed on there. I've got all my lectures since COVID basically because that's when I started using it. So I've got over 1,000 hours, and the most of the stuff is literal lectures, and some of them are summer lectures, which were like 3.5 hours. So there's literally 3.5 hour long videos on there. Uh, those might seem like they're really bad, but you can fast forward to the individual examples and get a lot out of it anyways. So I'll also have a list. It's called My Video List by Austin, and it'll have a date on it, and that has all the things I've made up to that date that's in the title. That will be in useful documents and links as well. Also in the unit in the module that is called useful documents and links, there will be the allowed equation sheet that you're allowed to use, as well as various fact sheets that basically are pictures of the inside cover of your textbook. If you actually had a physical hardcover textbook, Giancole had really nice layout on the front cover and inside, and then in the back cover and appendices with a lot of nice data, periodic tables, chart of nuclides, equations, all sorts of good stuff. I've made all those available to you in PDF form, and they'll be in there. And that's what you're given when you're actually taking a test. So I recommend you go ahead and take the time and print each of those out, and then use them every time you do your homework, or every time you take a practice test, or a chapter quiz, or excuse me, a chapter practice, or an online test, or a face-to-face test. So if you have those, by doing it that much, you'll have a good understanding of where everything is on your equation sheet, and it'll just be a lot better off for you. So that's about all of the big details that I wanted to show regarding the syllabus. So does anybody have any questions before we move on? Currently, the module's not up, but the module will come up probably tonight. It's called someone asked, how do you get the equation sheet again? So the module will say useful documents and links. And then one of those useful documents will say allowed equation sheet physics 241. And you click on it, it's a PDF. So you can just either download it or print it. Normally you have to download it before you print it, or it'll sometimes you'll have problems with it, especially if it's in Word. You can't really open up a Word document too often and then print it while it's open without downloading it first. So I do recommend you download it. The syllabus will be located in the syllabus link. It's just not there yet. I had some problems. We have a new syllabus builder, and it's not letting me make my calendar like I wanted it, so I couldn't post it. That should be posted tonight or by tomorrow afternoon at the latest. I will be posting an announcement, and therefore you guys will get an email when it's done. I apologize for that. It shouldn't have happened that way, but it did. And literally, it's only not happened that way maybe 5 times out of all the semesters I've been teaching here for 15 years. So it's always something. Uh, anything else? All right. Another thing. So this is 241. This course, you'll notice it when you get your book, it says Physics for Scientists and Engineers with Modern Physics. This course, if you took it at UVA or Virginia Tech or ODU, they usually teach it in a 3 semester sequence. So we would have 241, 242, 243, for instance. The 241 is what you're taking, and that's normally just Newton's laws of motion. And sometimes we'll cover some thermodynamics in that course as well. What we do here at TCC is we try to get a little bit into that 3rd semester stuff just in case someone does go from TCC to somewhere else and they have to take that 3rd semester. They'll have a leg up. So our idea is we cover chapters 1 through 11, then we skip and jump to 14 and 15. And then if I have time, I jump to 36, which is the chapter on relativity, special relativity specifically. So that gets us a little bit of what normally would be that 3rd semester. And then when we teach 242, I start at chapter 17 and I go up through 31. And then if I have time, I jump to 37, 38, 39, and 40. That covers quantum mechanics and nuclear physics. So again, that gets you into that 3rd semester. To be honest with you, I've had very little time to get beyond 1 or 2 chapters beyond the regular stuff. So the most important thing for you to understand is I have made those extra chapters as extra credit assignments in mastering So even if we don't get them, if you take the time to seriously try to learn how to do the chapter on relativity, for instance, you can get extra credit for it and it'll still help you even if I don't get to cover it. Okay. Now, that means the only homeworks that are automatically not extra credit are chapters 1 through 11, 14, and 15, and 36 usually. Okay. So those are not extra credit. If I don't get to cover 36, then 36 will turn into extra credit. But any chapters outside of those, even if they don't have an EC in the name, they're still going to be extra credit. I've made all those other chapters available now, and you have until 12/6 to do them. So you can do them as you wish, and you will get extra credit. The way those extra credit work is basically they just bring your homework average up to close to 100. So that's all those are for. And then, like I said, the practice test gives you up to a half a letter grade score improvement on your comprehensive final exam. So that's it far as that goes. Now we're going into chapter one. I'll give everybody one more chance. Anybody have any questions to ask me about anything I didn't cover? So those of you, if you came in late, you might want to look at the messages we've sent back and forth. In that, I gave my email. I told students what they had to put the subject line as. That'll also be in the syllabus. And I told everybody that they could only email me from their TCC accounts. And I also told them that they need to include their first and last name in any correspondence with me, whether it be by text or email. And then I gave my personal cell phone number for you guys in case you need to get to me really quickly or in case I didn't reply to your email within one business day. Uh, the other thing I said was everyone, when you first get in, you should go ahead and chat me your first and last name because I count that as role, as part of your role. Sometimes I do other things too, but as a bare minimum, that lists that you were there that day. So go ahead, whenever you first get in here, go ahead and chat me your first and last name. I can assign that to whatever username you're using in case you're, trying to hide your identity a little bit or whatever. You don't want the man catching you or whatever. Okay. So now, I'll apologize. I have a really bad sense of daddy humor, so all my jokes are dad jokes. And not only that, I pretty much perpetually stopped learning in 1980, so all my jokes are related to the 1980s. That means none of you were alive at that time, probably. So, uh, now, this first chapter is called Introduction, Measurement, and Estimating. And the subsections you'll see are 1.1, How Science Works; 1.2, Models, Theories, and Laws; 1.3, Measurement and Uncertainty; semicolon, or actually this is a semicolon, significant figures. 1.4 is units, standards, in the SI system. 1.5 is converting units, which is a very important part here. 1.6 is order of magnitude, rapid estimating calculations. And 1.7 has an asterisk by it. Normally, the asterisk means that the author says this section is optional. In this particular case, I am not calling it optional. So that unit analysis and dimensional analysis, that is a required section. That's a way where you can I can tell you, for instance, the period of a pendulum is measured in units of seconds. And I'm going to tell you that it depends on the length of the pendulum and the gravitational acceleration of the planet that you're on. Now, use dimensional analysis to figure out a formula for the period of that pendulum. And you can do that. And turns out you'll get the right formula up to a factor of about 6.28, which y'all probably recognize that as 2 pi. So, and of course, one experiment would immediately show you that you're off by a factor of 2 pi, and you would correct that immediately. But sometimes you even get it exactly right. For instance, I could give you, I'm going to tell you that energy depends on mass and velocity of light. And if you do dimensional analysis of that, lo and behold, you'll get E equals mc squared is the formula. So it's a very, very valuable tool. It's something that we do use, so it's not going to be optional. I usually don't get a chance to cover, to talk about all those sections or even to list the subsections, but I do tell you when I'm going to omit a section. And then the other thing is right after that in the chapter, there's a chapter opening question and it says guess now. I'm not always going to tell you to do that, but you should always do that before you start reading that chapter. You might not have any clue, and that's just fine. But what you want to try to do is read that question, and it's normally multiple choice, and you want to use something to try to reason out what you think the answer is. If you have nothing to base your reasoning on, then just take a guess. It's okay. All right. And not only that, it's not bad to get a wrong answer. In fact, most of the scientific discoveries that we've made have come because someone made a errant hypothesis, a wrong hypothesis. So you learn more from being wrong than you do from being right. So it's perfectly fine to make a bad hypothesis. Never be afraid of making a wrong hypothesis in an experiment either, for instance. So do that, and then as you read, it gives you something to look for and to pay attention to the words because later on in the text they're going to supply the answer to that guess now question. Okay, so do that. It's called chapter opening question, and normally they have one or two. Sometimes they'll have five. If you're looking in the textbook at this time, and it is normally good if you have your Pearson website open and the e-text open as we're going, because what I normally do is work straight from the examples in the book, but I don't put them on the screen because then that would be a copyright violation and I have all sorts of problems. But I read them out loud, and that may or may not be, but it's a lot harder to find me doing it. And then I work them out, the examples as they are. So if you have the chance to have the book open while you're looking at the examples, it'll be a little easier for you. But you'll notice the first figure in chapter one is a bridge over the river Tiber in Italy. That's a bridge that was built over 2,000 years ago and it's still standing and quite strong. And then immediately below it is a picture of the Hartford Civic Center, which was built in 1978 and collapsed 2 years later. So that gives you a little idea of the importance of when we do these calculations. Not only do we have to do calculations to get an estimate of what the right answer is, we also need to know how far or how varied our answer can be. In other words, what is the uncertainty in that result? And that's part of what this chapter is about. It's not only about being able to calculate the right answer, it's about being able to calculate the right answer and then what are the error bars on that right answer. Like if you get a number that's markedly smaller than that number, does that refute your hypothesis or does it support your hypothesis? Or if it's monumentally larger than the predicted answer, does that refute your hypothesis or does that support your hypothesis? Well, the rule for that is if it's in the error bars, then we assume that it basically supports the hypothesis. If it's outside the error bars, then we assume that it refutes it and we have to throw it away. In other words, we have to either completely throw the hypothesis away or we have to massage it to make it work better. Okay. So that's part of what we're talking about here. And we're going to go on to how science works. Your book talks about hypothesis and theories, and it's using some old language that I would prefer not to use, but mostly we're in sync with our ideas. I'll tell you that the word theory in most modern applications nowadays means something that's super, super strong, supported by evidence, supported by butt tons of evidence. That's the official unit created by the SI system that I just made up. Okay, so it's a butt ton of evidence. For instance, okay, the special theory of relativity is probably the single most tested theory in the history of mankind, and it's never once been found to be an error. And I'm talking millions upon millions of tests, so millions of millions, not just multiples of millions, but millions multiplied by millions. Because we have, for instance, in particle accelerators, we have computer codes that detect outcomes, and they look for things like violations of special relativity. And when those things are running, they have, on the order of thousands of collisions every second. And we as humans can't analyze all that, so we let computers do it. And the computers look for violations of special relativity. And they've never found one that stuck. We have had a couple labs. In fact, there was about 10 years ago, someone detected neutrinos traveling faster than the speed of light, but we later figured out that they had just screwed up in their analysis. So we don't expect it to be, but it literally only takes one well-done experiment that someone else can repeat, and that just throws it all away. But the main thing is once you come up with some kind of hypothesis and then you go through the prediction, observation, prediction, observation, prediction, observation, prediction. Once you go through that cycle tens of thousands, hundreds of thousands, millions of times, then that hypothesis graduates to what we would call a theory. Okay. It means it's never once been contradicted and it's always been found to be consistent with reality. At that point, it's a full blown theory. And your book says theory is a bigger thing. So it has a lot of accoutrements to it. Like the special theory of relativity isn't just a single equation, it's actually two fundamental principles. The laws of physics are the same for all inertial observers, and the speed of light is a constant independent of the motion of the source and the motion of the observer. That's a little bit bigger than just an equation. So he's trying to say you have equations which can be treated like hypotheses, and they, in some sense, could go through that cycle a bunch of times. And in my estimation, they would be called a theory, but in his, they would still be something like a part of a theory. So he's saying there's a certain bigness to theories, like the theory of evolution isn't just a single thing, or the theory of gravity isn't just a single thing, that sort of thing. But just remember, no one should ever say that's just a theory. If they're saying it in a diminutive way, the just should be in front of something like hypothesis. Okay? So that's something key to work out. I will tell you that all of the practice tests and the online tests and all that stuff, those should be answered based on not what I'm saying. I'm giving you extra information about this particular part, but specifically, it should be more about what the textbook says. So just keep that in mind, and I'll point out some key areas, and like I'm doing right now as we go along. But that's about an idea of how science works, and you'll read a different scenario of that in the book when you read that subsection. Then we go into models, theories, and laws. Again, that's more of what I was just talking about. Theories are invented. They're not discovered. And again, that's where he's taking a bigger idea of theory than just any hypothesis that could ultimately turn into a theory. But again, that's where him and I differ. But you're going to answer all your practice test questions and stuff based on the reading of the book, not that. F equals ma, for instance, is a relationship, and we call that a law. He makes a difference, an estimation between a difference and a law, where they're more or less the same thing. So keep that in mind. We're going to move on from that because these are just stuff that you'll get from the reading. We're going to move on to measurement, uncertainty, and significant figures. Are there any students here? Y'all can chat me if you did. Any students in here that are not familiar with sig figs or significant figures or significant digits? Any of you? All right. Well, that's a good sign. So and there's going to be a document either in module for chapter one, or it'll be in useful documents and links, or it might be in both. But there's going to be a document that tells you about scientific notation, or excuse me, about sig figs. And I'm going to give you these rules right now, and that's where they come from. I'm not your lab instructor. I'm not teaching any labs this semester, but this will come in handy to you in whoever you have for lab. So here's my rules for sig figs. Uh, First off, the leftmost digit in any number, is called the most significant digit, MSD for short. Okay. The if there is no, now I'll go ahead and do this way. See, so the first rule was the leftmost non-zero digit is the most significant digit. Okay, the leftmost non-zero digit is the most significant digit, and therefore it's the MSD. If there is no decimal present, then the rightmost non-zero digit is the least significant digit, the LSD, if you will. So again, if there is no decimal present, the rightmost non-zero digit is the LSD. Then the next rule is if there is a decimal present, then the rightmost digit, period, not non-zero digit, just the rightmost digit is your LSD. And then the fourth rule, let me repeat that one. If there is a decimal present, the rightmost digit is your LSD. And then the fourth rule is your MSD, your LSD, and all the numbers between them are significant digits. So that's the way you can go about figuring out how many sig figs a number has. Then to use that, if you multiply two numbers, then what you do is you count the sig figs that the numbers have in them. And if one number has a smaller number of sig figs than the other, then you have to round your answer to that number of sig figs. So your answer to any division or multiplication problem is has to have the same number of sig figs as the number that went into the calculation that had the fewest sig figs. Okay. Additionally, if you have to take a cosine or a log or raise e to the power of some number, then the answer should be to the same number of sig figs that you put into it. So if I raised e to the 1.34 power, since 1.34 has 3 sig figs, I should round that answer to 3 sig figs. If I take the cosine of 0.0123, which also has 3 sig figs, then I should round that to 3 sig figs. Now, the only thing that makes it complicated is when we go to addition and subtraction. If you go to addition and subtraction, we don't use sig figs anymore. We use the precision of a number. So precision is the ability of our ability to measure a number and get something comparable to the same number no matter how many times we measure it. So if we can consistently get exactly the same number, then we have a 100% precision, if you will, even though that 100% doesn't really mean anything. Okay. It's just a matter of saying, hey, I measured this one quantity 80 times and I got exactly the same number every time. That means there's a high level of precision. If I measured it 80 times and got 80 different numbers, chances are, unless those numbers are really, really close to each other, chances are that's a low level of precision. The way we indicate that is by the number of decimal places, because what we have to do is we have to calculate something called the standard error or the instrumental error, and the bigger of those two is what we have to keep. And then we write that after the number with a plus or minus. So if I had, for instance, the number 1.23, that's understood to have an uncertainty of plus or minus 1 in the last digit. So I would call that 1.23 plus or minus 0.01 meters. That 0.01 is either the instrumental error, because that was bigger than the standard error, or it's the standard error, which is a statistical calculation that we do. And the way we round that number so that we called it 1.23 was that rounding spot had to line up with the first digit in that uncertainty. So the fact that the uncertainty was 0.01 meant that we couldn't carry the number any farther than 2 decimal places, because if we've got an uncertainty of 1 digit in the second decimal place, we have no hope whatsoever of knowing what the third decimal place is. Does that make sense? Anybody have any questions on that? There will be examples in the document that I show you, and your lab will go over this as well. So we're not going to deal with it too terribly much. I don't even grade in sig figs. I'll tell you, for instance, if you take a test in my class, unless I explicitly tell you otherwise, you should probably just report everything to 3 sig figs, and you'll be fine. Sometimes you'll need more because if I ask you to compare two quantities that are supposed to be different and you do 3 sig figs and they're exactly the same, then you might have missed the point. But other than that, pretty much 3 sig figs works across the board. And I'm never going to take off for sig figs unless it's explicitly a question testing you on your ability to use sig figs properly. Okay. And you'll see that those do happen in the chapter 1 homework as well as the chapter 1 and 2 practice test and chapter 1 and 2 online test. So now back to that precision, because the standard error dictates what decimal place we round numbers off in, then the precision is a measure of how many decimal places we have. So for instance, if I say a number like 500, then that either has only the hundreds place because that's where the 5 is, or it might have the tens place because maybe that first 0 is a sig fig, or it might have the ones place because that second 0 is a sig fig. But it definitely doesn't have any others, so it's at least only to the nearest whole number. Now, if I said the number was 500.1, then that would be to one decimal place. If I said the number was 500.02, then it'd be to two decimal places. So the 500.02 is more precise than the 500.1, and the 500.1 is more precise than the 500. The 500 is more precise than 5.0 times 10 to the 2, and the 5.0 times 10 to the 2 is more precise than 5 times 10 to the 2. Okay, so that's what I mean by decimal places being precision. So the rule when adding and subtracting is if you add two numbers, the number that's known least precisely dictates the precision of the answer. So if I add 12.12758 and 12.01, then I have to round it to two decimal places no matter what. Does that make sense? All right. So that's pretty much all you really need to know about that. I will tell you that sig figs is not really a good scientific measure of what you're supposed to do with numbers when they have error in them and you use them for formulas. The proper analysis is called propagation of error, and you probably should have a lab this semester and in the 242 course in which you cover propagation of error, and there's much more robust formulas that we use for that. If you have any questions about that, by all means ask me, even though I won't be covering it in class. Okay? All right, so that's a discussion of measurement, uncertainty, and significant figures. Uh, I think you can get most of that from the reading. They do have a conceptual example 1-1 that says significant figures using a protractor, and they tell you to see figure 1-4. You measure an angle to be 30 degrees. A, how many significant figures should you quote in this measurement? And B, use a calculator to find the cosine of this angle. So if you look at this figure 14, figure 1-4, you'll see it's a protractor sitting on graph paper, and it's got a little red line and another red line that marks an angle, and it does appear to be right at the 30. If you look closely, though, you'll see that the smallest measurements on this protractor are actually not whole degrees. It's actually half degrees. The reason, or the way I know that, is I look at 20 and 30, and I see the big spaces between 20 and 30 add up to be 10. There's 10 spaces between 20 and 30 of the big variety. But if you look closer, each of those big spaces is cut in half. So they're really marking it down to the nearest half a degree. So that's kind of a questionable point. It's an error of 0.5 degrees in that case. So it's not really fair at that point to write it as 30.0 degrees because the uncertainty is not plus or minus 1 in that last digit, that 0.0 or 0.1, it's 0.5. So they would say it's best to go ahead and call that 30, period. Okay. And then when you take the cosine of that, you get 0.86607, something like that. And of course, since it only has two sig figs, you should only call that 0.87. And that's the way that process works. Remember, whenever you take a function of a number with sig figs, the result should be rounded to the same number of sig figs as you put into it. And when you multiply two numbers or divide two numbers or divide any number of numbers or multiply any number of numbers, you have to round it to the number of sig figs that the number that had the least had. Is there a difference between 30 and 30.0? Mathematically, that's an excellent question, by the way. It's normally one of the questions I ask my students. Mathematically, 30.0 and 30 decimal point are exactly the same. If you do a subtraction of them on the calculator, you get 0, right? But physically, they're entirely different. For instance, if you're talking about 30 millimeters or 30 microns, let's think about that, 30 micrometers, that's a millionth of a meter. If you're actually talking about that, if you go to a machinist and say, hey, I need this specified down to the nearest whole micron, then that'll cost you a certain amount of money and it might be kind of expensive. But if you instead tell them, I'd like that to be down to the nearest zero point 0.1 microns, that's going to cost you a factor of 10 more probably. So if it cost you $500 before, it's probably going to cost you 5 grand now. And if you go another decimal place still, it might cost you another factor of 10, but it might even cost you another factor of 100. So in that sense, those two numbers are very different. Oh, and he's referring to the decimal. So according to my rule, which is a little bit tricky one, but it's the one that I like the most. If I write 500 with a decimal point after it, then that has three sig figs. If I write 500 without the decimal, then that has, according to your textbook, and this is important because you'll see this question on your practice test and your online test and probably your face to face test. If they give you a number like 500 and they ask you how many sig figs it has, the answer is ambiguous. Okay. That's what the author's teaching you. My sig fig rule says that's not ambiguous. There's one sig fig in 500. But if you write 500 with a decimal point after the second zero, then it has three sig figs. If you write 500 with a zero, with a decimal and then a zero after it, then it has four sig figs. Good question. Actually, both questions were good. He said he actually meant the other way, the part about the decimal versus no decimal. So yeah, according to my sig fig rule, not writing a decimal point is very relevant to write to the number of sig figs. The number you have when you write 30 is ambiguous in terms of the number of sig figs, according to your textbook author. According to my rule, though, the number 30 with no decimal place has one sig fig. And that sort of thing. So if you actually had the decimal, though, you had 30 point, then by my rule, that's going to have two sig figs. Any questions? All right. We will be using scientific notation. You can use engineering notation. What I will tell you guys, though, is if you ever have to write like a really small number in longhand form without scientific notation, like 0.0000, something like that, then put those numbers in pods of three so it's easy for me to determine how many zeros you got and it's easy for you to determine it. It's very important. So if you wanted to write a number, you might write it as 0.000 space 072 space 145, something like that. So by putting them in pods of three, it makes it easier for us to see. And you don't have to always have the pod right up against the decimal. If you have to start it from the other end, that's okay, as long as you've got it in pods of three. And there might be one that has a pod of two. I'm not going to take off any points for that. I just want you to put it in increments of three so I can quickly tell how big the number is. Everybody follow that? Everybody tracking on that one? If you have any problems with with scientific notation, that's probably something you want to ask me directly, either in an office hour, which is what I have at the end of this class every Monday and Wednesday. But that's something you can do, but it is something that you should definitely get addressed if you don't know how to deal with that now. So we'll go on from there. It does talk about percent uncertainty, which is the same thing as fractional uncertainty. You'll get that in your lab as well. One thing I will point out, like your book does in here, I actually highlighted, ooh, it doesn't seem to have stuck here. If someone tells you a number is 97, okay, then what you're supposed to do is assume that the uncertainty is 1 in the last digit. So the uncertainty in 97 is plus or minus 1. The uncertainty in 97.4 is plus or minus zero point 0.1. The uncertainty in 97.25 is plus or minus zero point 0.01. Now, if I tell you otherwise, then that digit might not be 1. It might be 2 or 3 or 5 or 7 or something like that. But if I don't tell you anything else, your job is to assume that the uncertainty is 1 in the last decimal place. That's going to come in handy too, as you'll see in some questions that get people on their practice test, as well as their first online test, as well as their first face-to-face test. So that's another big warning. Uh, and your book talks about accuracy versus precision, and it talks about the importance of percent uncertainty and fractional uncertainty in realizing that sig figs are not the be all and end all. They're not really what's sufficient for science to be done. When you're actually doing scientific measurements, you have to use these propagation of error formulas, not sig figs. Sig figs are sort of just a first order approximation, and your book even shows you examples where they get it wrong. Okay. All right, let's move on to your book did say, as I told you, precision is how consistently you can get the same number when you're measuring something. That's the measure of your precision. Accuracy is how close your result is to an accepted value. So accuracy is something you get by, for instance, taking a percent error between your result and the known result, for instance, for the gravitational acceleration of the Earth, which is 32 feet per second, or 9.80 meters per second. If you're comparing your value of G to 9.80, then you're talking about accuracy. If you're comparing your different results from 5 different trials of G, then you're talking about your precision. Y'all see the difference there? Anybody have any questions on that? Okay, it looks like everybody's good on that. So the next part we're going into is units, standards, and the SI system. So in this case, I want to tell you that it's not only important that you give me a number for an answer, it's also important that you know whether that number is what we call a denominate number. I know that's a word that most people don't know, but you probably recognize it because you've probably heard the phrase denomination before. So, for instance, the denomination of a $5 bill is $5. Okay, or dollars is the denomination. So, a $1 bill is a denominate number because, or a $1 is a denominate number because it has a unit of a dollar. So that's what I mean by denominate numbers. There are pure numbers like pi, which you recognize as the circumference divided by the diameter. And you can see if you measured the circumference in inches, then you probably needed to measure the diameter in inches as well. So when you take the circumference in inches and divide it by the diameter in inches, the units cancel out. So you have no units. That's why pi is considered a pure number. And those numbers are important as well. It's just you need to always express the unit if it has one, or you need to express it without a unit if it doesn't have one. And thirdly, you never want to put the wrong unit on it. Like if it's a 1 meter, I want 1 meter there, not 1 second. Okay. So that's another key aspect. But in order for us to have those denominate numbers, we have to have some system of measurement that everybody can agree upon. That's what the SI, the System International, is, and that's the descendant, if you will, of the metric system. The metric system was more or less what came up from rationalizing the number system as we had, because we had this British system that, by the way, only the United States and like Liberia, they're the only two countries on planet Earth that still use the British system. It's not a good system. It's so bad that literally I worked in structural and civil engineering and wastewater engineering and electrical engineering and computer engineering. And I kid you not, they're using MIPS and PIPs and MIPS and KIPs in there. Anybody know what a MIP or a KIP is? It's kind of funny. A MIP is a megapound, and a kip is a kilopound. So literally, they're using the prefixes from the SI system, but they're using them with the stupid British system. The whole reason we got rid of the British system is because they were historical measurements. Like the gallon is made up of 4 quarts, and a quart is 2 pints, and a pint is 16 ounces, and a cup is 8 ounces. So one pint equals 2 cups. And if you ever have to try to figure out the gas to oil ratio for your weed eater or your leaf blower, you're going to have to know 50 to 1 and 40 to 1, and you're going to have to use that stupid big G with the 4 Q's and the 2 P's in it and all that stuff to figure out the right units. That's an ugly system. The beauty of the SI system is that you have a base unit like a meter or oddly enough, they do a kilogram. That's the base because the gram's too small, but that's got a prefix on it. But either way, we pretend that's the base unit, and that's what you have to use in mass for any of the equations we're doing in physics. And then we have the second. That's another base unit. But if you want 1/10 of a second, which is a easy thing to do, you just move the decimal one place to the left. Well, that's called a deci. That's called a decimeter. If you want 100th, that's a centimeter. If you want 1,000th, that's a millimeter. If you want one a millionth, that's a micrometer. If you want 1 billionth, that's a nanometer. And if you want 1 trillionth, that's a femtometer, I think. No, picometer. Sorry about that. Yeah, that's a picometer. So that's a really rational system. Everything differs by a factor of 10 or some power of 10. They go by units of one power of 10 for the first three, and then they jump three every one after. So getting smaller, it goes deci, centi, milli, space, micro, space, nano, space, pico, space, femto, so on and so forth. When you're going bigger, you can have 10 cards or you can have a deck of cards. That's funny, right? This is a dad joke. Come on, deck of cards. But literally, that's the prefix, DEKA, and they use a capital DA for the prefix. So DA cards is a deck of cards. That's 10. If you go up by another one, then that's a hecta. And then the next one is a kilo. That's 1,000. And then space, a million, which is mega, space, a billion, which is giga, space, a trillion, which is tera. So that's the metric system, and that's the way we use those units. I'll write that up, and you should make up a mnemonic to remember just from T, and I actually normally write it as T being on the left and the small being on the right, and I make up a mnemonic, and it's always me being stuck in fifth grade, so it's always got something about poop or pee or something stupid like that. So I recommend you guys make up your own mnemonic for that. We've actually covered everything I planned on going over today. We didn't work any examples. I will be posting because we're going to cover a chapter a week. I will be posting in the chapter one links to YouTube videos that cover all of chapter one. So even if I don't get through all the material, you'll still have access to video examples of all the material. But I'll cover a lot more next time. I had to cover, the syllabus, and that just takes a nightmare amount of time. So you guys are free to go. This is now an open office hour for all of my classes. So you guys are welcome to stay as late as you need, and I'll answer questions, but you're free to go. Make sure you chatted me your first and last name already if you haven't already done so. But have a good one. And I would say try to finish reading all of chapter one by Wednesday. That would be a great thing. If you don't get all of chapter one, it'll be a little bit harder for you to follow, but that's plenty good. Thanks for coming, everyone. We'll be sharing the practice problems so we know how to do the problems. Uh, Yes, yeah. There's a ton of practice problems that I do actually on the syllabus. I mean, on the videos as well as in class. So I'll do nothing but examples next time. I'll explain a little bit of theory behind it, but I'll do nothing but examples next time. And the same thing with all the videos I post. I have a ton of videos of me solving various physics problems. Some are really super complicated and use a lot of calculus, differential equations, linear algebra, all that stuff. But other ones are just, straight algebra and stuff like that. So you'll get a lot of experience to seeing a lot of different practice problems. Chapter one is on Pearson. Yes, it's in the e-text area. And remember, read it in those small intervals of time until you get better at reading for longer intervals of time. It doesn't do you any good if your mind is wandering while you're reading. You're just getting through it, and that's not helping you. Thank you. You have a good night too, Jordan. Anybody have any questions? You speak right up. I You can always do that, by the way. You don't have to like raise your hand or anything. You can just say, "Hey, excuse me, Mr. Younger," during class, and anytime you have a question, I'll be glad to answer it. If it becomes too cumbersome or something, I'll say, "Hey, can we save this to the end?" But generally, it never gets that way. And sorry, you guys that show me your faces, you're normally the ones I'll call out as examples, as you saw, Steve. It doesn't help that you have that Isaac Asimov beard. Are you familiar with Isaac Asimov, Steve? There you go. Excellent. Good sci-fi writer. Where do we find the Zoom recordings like this one? They'll be on my YouTube channel. Don, I'm going to write it again here. It's actually in the chat, but I'll write it again here. www.youtube.com/at physics solutions dot com. So that's my YouTube channel. You can click on there and you'll find it. Normally, it'll have in the little box down below the picture, there'll be a description and it'll say like PHY 241 N02B, and then it'll have 08242026. That shows you, hey, this is August 24th, 2026. So you'll know immediately it's that one. Not only that, when you go to my Google Docs, you can do a search for that string of characters, and then I'll pull up the actual notes that I took. There were no notes on today, so that won't be relevant. But there will be notes on future ones. Anybody else? You're welcome, Don. Or yeah, Don. How about you, George? You got a question? By the way, guys, if y'all see me just start talking and I'm not wearing this, y'all might want to remind me because I've went through about 5 minutes of class forgetting to put on my headphones. And like, I can't hear my students. I don't know. And they're like, oh, I can hear you. And so it's just me being a goober. You know how much about the labs? There's a Canvas page, but no date. Yes. I've taught the labs every semester I've been here. This is the first time I've ever had a semester without labs. So I've done all the labs that they're doing. We've got a new person covering one of my lab sections and some other people that are very familiar with our TCC system teaching the other labs. So they might just be waiting until they get a better idea of what's going on. But normally you're going to have a lab every week, and it's normally due by the beginning of class the next week. And they'll post the actual lab document. At least that's the way I've always done it. And most of the people I know of do it. They'll post the lab document in your Canvas page for the lab, and you can just download that as either a Word file or a PDF, and you can type your data right into that. Different instructors do it different ways, but that keeps us from having to print, and then you return the document as an electronic file as well, so you never have to print anything out. But definitely ask your instructor about that directly. You should be able to find their name as well. If you can't, just send me a email or send me a text message, and I'll look it up for you and find out how you can get in touch with them. No problem, Steve. I see you've got a mask on. That picture's not going to help me very much. All right. Well, that looks like it. Thanks for coming, everybody. Bye bye.